Hello everyone, I'm going to share with you our CVPR 2023 paper, Class-Incremental Exemplar Compression for Class-Incremental Learning. This work is done by Ziling, Yao Yao, Bernd, Qianru. First, I would like to introduce class-incremental learning. In this task, different classes arrive in different phases. In phase 1, we have data 1 and chain A classifier 1 on data 1. Then we test the chained classifier 1 using test data 1. In phase 2, data 1 is not available and the data 2 arrives. We initialize another classifier 2 using the parameters of classifier 1. Then we chain the classifier 2 using data 2 and test it on both data 1 and data 2. Similarly, in phase 3, data 1 and 2 is not available. We chain classifier 3 on data 3 and then test it on data 1 plus 2 plus 3. The target of class-incremental learning is to obtain a good average test performance for all learning phases. One big challenge of class-incremental learning is catastrophic forgetting. Take phase 3 as an example. Because classifier 3 cannot access data 1 and 2, it will easily overfit to data 3 and lose the knowledge of data 1 and 2 during training. In test stage, it shows low performances on data 1 and 2, and this phenomenon is called forgetting. One important branch of class-incremental learning methods is based on exemplars. The very first work is iCal. It maintains a fixed size memory to store all the class samples as exemplars. These exemplars can be replayed in subsequent phases, and the forgetting problem is mitigated. Additionally, with a limited memory capacity, iCal uses herding technique to select representative exemplars. The following works propose to optimize the memory in terms of exemplar quality or quantity. Mnemonics directly optimizes the image tensor so that one exemplar carries more information, while the number of saved exemplars is not changed. MRDC chooses to compress exemplars with JPEG algorithm. Then each exemplar takes less memory consumption, and more exemplars can be saved. However, the blurry exemplars also lose part of classification discriminativeness, which introduces a trade-off between exemplar quality and quantity. Class-incremental masking. The method proposed in this paper adopts pixel-selective compression strategy and applies adaptive compression for dynamic class-incremental learning environments. With this design, scene-based CIL can compress exemplars without losing much discriminativeness. To achieve this, our core idea is to downsample only non-discriminative pixels. Specifically, we use the class activation map to split discriminative and non-discriminative pixels. The map can be obtained by multiplying the feature block output of image X and the classifier weights of label Y. We apply a threshold tau to the normalized map and find the tightest bounding box, capital B, around one valued pixels. We treat the pixels outside capital B as non-discriminative ones. We downsample these pixels with a ratio eta and finally derive the compressed image X hat. The storage consumption of X hat is always less than 1 unit. We further apply adaptive compression for dynamic CIL environments by generating compression masks. with the SIM module. The SIM module appends a new forward path on the feature extractor by plugging in learnable pad activation units. Please note that other weight layers are shared with the original path, so the SIM module introduces few additional parameters. Then we use the appended path to produce compression masks. We organize the optimization of the whole model into two levels. The task level optimization addresses the current task, and the mask level optimization is to search SIM parameters file to produce adaptive masks. Specifically, we formulate the latter as a bi-level optimization problem, where in inner step, we take an update step on theta using data compressed by phi, and in outer step, we validate this temporary theta on uncompressed data, and the gradients are backpropagated to update phi. Another two regularization terms, memory constraint and the mask diversity loss, are also applied in outer step update. The proposed method serves as a plug-in module to baselines. Comparing with SOTA, it achieves consistent performance improvements in multiple settings and datasets. The results on ImageNet 1K show that the proposed method can bring larger performance improvement under stricter memory budget. The ablation study validates the effectiveness of the compression framework and optimization pipeline. For the hierarchical analysis on different size objects, we find that the proposed method achieves larger compression rates and a performance boost for small objects. Thanks for listening. If you are interested in this paper, please kindly scan the QR codes for more details.